Hi, welcome to this TTK tutorial. In this video, I'm going to show you how to reproduce one of the examples shown in the gallery section of the TTK website. So let's go there. In particular, I will show you how to reproduce this example here, the Morse Smale Quadrangulation demo. So for this, you will first need to open a terminal, like I did here. And I will assume that you successfully installed TTK and that you downloaded and decompressed the TTK data package to this directory, TTK and TTK data. So let's go there. Alright, so now we'll run the demo by typing the following command. review states Morse Smale Quadrangulation.pvsm, and you hit enter. Alright, so this will take a few seconds to compute. Alright, so here we are. So what you see here is a demo example for the remeshing of a surface made of triangles on the left into a surface made of quads on the right. So I will zoom in a little bit such that you can see what's going on here. So basically the input is on the left, is this surface made of triangles, and the output is on the right, this surface made of quads. Alright, so this kind of remeshing can be fairly useful in practice for applications in engineering and in the entertainment industry as well. So to make this happen, we'll leverage TTK to compute a specific type of quad mesh derived from the Morse Smale complex of a smooth function. And here we use an eigenfunction of the Laplace Beltrami operator, which is something pretty standard to do. So the Morse Smale complex is this representation of the surface that you can see to the left. And here the spheres are the critical points of the smooth function that we consider. So in green you have maxima, in blue minima, and in white saddles. And the white curves are the separatrices of the gradient flow. So those are integral lines that follow the gradient and which connect critical points together. And here in the background the coloring corresponds to the 2D cells of the Morse Smale complex, and each cell is shown with a different color. And you have the property that for any point in a given cell, you're guaranteed to integrate forward and backward to the same critical point. So if I take a point in this green cell, I integrate the gradient forward, I will end up in this maximum, and downwards into this minimum. And this is true for all the points in this cell. All right. So for quad meshing, there's a particularly useful property of the Morse Smale complex that we'll use here, which is the fact that in 2D, the cells of the Morse Smale complex are already quads by construction. So to produce a quad mesh, in principle, we just need to refine the quads that you see to the left to have a valid quad mesh. Alright, so as a user, you can control the meshing process at several levels. So first, you can control the level of subdivisions of the quads that you have on the output. So let's modify this. Let's say we want only 2 levels of subdivisions, and you can control also the level of smoothing that you want on your quad mesh. So you hit the apply box. Alright, and here you see that you get a coarser quad mesh. Another useful thing that you can control in this process is the fact that you may want to extract either a primal or a dual quadrangulation. So for this, you need to play with this checkbox here. So let's uncheck it. So in the primal mode, the quad mesh generated by the Morse Smale complex will exactly align with the separatrices that you see here. So this means that the algorithm will take each of the quads that you see and subdivide them to produce the output. So what this means is that the quad flow in the output will be aligned with the separatrices of the Morse Smale complex, like you see here. And if you check this box, it will construct a dual quad mesh. And for this, it will take each saddle point, look at the neighbors, and connect the neighbors in a sequence. And here, this is possible because you have the property that each saddle point will have exactly a valence of 4. So the output mesh is constructed by linking the 4 neighbors of each saddle point. And then you can refine it further, as you see in this example. So in the output, the outcome is that the quad flow will no longer be aligned with the separatrices, but with the diagonals of the cells of the Morse Smale complex. So it will be aligned with this axis and this axis, as you can see here. All right. So in this pipeline, the input function that we considered on the surface is an eigenfunction of the Laplace-Beltrami operator. But you could use something else if you wanted to. And the same remark goes for the quad subdivision process. You can provide custom coarse quad meshes that you may want to subdivide. So the cool thing with the eigenfunctions is that they usually are computed as a batch. So you usually have a family of functions that you can explore to produce different quad meshes if you want. So let's have a look here. So for instance, here we're looking at the function 83, but we can interactively iterate over those functions to look at the different possibilities of quad meshing. So here, this would be the mesh generated with the eigenfunction 84. Let's have a look at 85. So this is how it looks like. And in general, we'd recommend to go by default for high eigenfunctions. So let's have a look at 95, for instance. All right, this is how it looks like. So if you're happy with this result, you can take the output here, the surface, and you can save that with the menu file, save data, and then you can call that output.off, and you can select the OFF format, which is somehow pretty standard for storing quad meshes. You can click on OK. Right, so now we'll show you how to reproduce the exact same pipeline, but with a different object. So for this, I will close this window, then we'll open PowerView. All right, and I will go to File, Load State, and I will select the state Morse Smale Quadrangulation. Okay, and here in this menu, I will choose the entry Choose File Names, and I will select another file that I prepared, and I will click on OK, which is another model for which I pre-computed the eigenfunctions of the Laplace-Beltrami operator. So this, again, will take a few seconds to compute. All right, so here we are. So this is the different model. This is kind of a statue, but the exact same pipeline has been applied with the same parameters, and this is the output that you see for this these remeshing parameters. Okay, so again, as before, we can play with several parameters. Let's say that we want to reduce the level of subdivision to have coarser quad meshes, and let's say that we want to have a look at the primal quad mesh. Let's click on Apply. And here is the result. And again, if you want, you can explore different eigenfunctions. Let's say we'll go for, let's go for 150. Apply. All right. And this is the quad mesh that we get, the output. All right, so now if you want to apply this pipeline from your own code, you have several options. So you can save the state and select the Python extension, so that will convert this entire pipeline into a Python script if you want to do some quad meshing with Python. And in the following, I will show you how to reproduce this exact pipeline from scratch by opening PowerView and applying all of the filters here one by one. Because if you want to use this quad meshing capability in your own code, basically each of the green boxes that you see here correspond to an object that you will have to instantiate in your code. All right, so let's close this and let's restart. So for this, I'll open PowerView, and I prepared already a triangle mesh. So let's open this. Okay, so this is the input triangle mesh. You can see these are triangles. So the first thing to do in this pipeline is to compute the eigenfunctions of the Laplace Beltrami operator. And since this is kind of a long process, what we'd recommend here is to do it once for all and then save the output of the computation to disk for further interactive construction of the quad meshes. So to compute the eigenfunctions of the Laplace Beltrami operator, you can go to Filters and then select the appropriate TTK filter for this, which is here, TTK eigenfield. Or you also have the opportunity to search. In Linux, there's a keystroke, Control and space, to have the search bar, and you type the keyword that you want to apply, and then you hit Enter. In here, like I said, we recommend usually to have a high number of eigenfunctions, so let's go for 500. Then you click on Apply, and this will take a few minutes. Alright, so now the computation has finished. So we can take this and store it to disk now. So I forgot to mention, but to make sure that this feature is enabled in TTK, you will need to make sure that the optional dependencies of TTK are installed. In particular, you want to make sure that the spectra, the dependency, is installed, which is what is used under the hood to compute those eigenfunctions. Alright, so now we'll save that to disk, save data. My test example here, .vtu. Alright, if we replace that, okay, and off we go. So we can close PowerView now, and we'll open it again on the file that we just computed. So let's go for it. Alright. Okay. So the first thing that we do here will be to select one of the eigenfunctions to compute. So for this, you go into the filters and you go for search for a specific filter that you want to use. And here we want to extract a component of the vector of eigenfunctions. So you want to use extract component. Enter. And here a function that should be kind of relevant for this example is the eigenfunction 83. Let's go for it. All right, so let's see the outcome. So this is the scalar function that we'll consider for remeshing. And here already with the color scheme, the color map here, you have a sense that there is a sort of alignment that is kind of interesting for the subject. So what we'll do now is to compute the Morse Smale complex of this function, but often it may happen that you have some spurious features that appear in the function, and these may be due to numerical instability in the solve of the eigenfunctions. So what we'd recommend to do before computing the Morse Smale complex is to compute some simplification of the function to remove the noisy features first. And most of the time this is not needed, but we'd recommend to do it just in case you run into those issues. So what we'll end up doing here is to compute something that is called the persistence diagram that measures the importance of the critical points, and will only maintain the most important critical points, and we'll simplify the data according to this, and once we have this, we'll compute the Morse Smale complex. So to make sure that the simplification is consistent for several eigenfunctions, what we'll first do is to normalize the data. So here I will hit Control and space, and I will call the normalizer. So this will normalize this function between 0 and 1. And next, I will compute the persistence diagram to have an idea, a sense of the importance of the critical points. Go for diagram. And here I'll check this box, embedded in domain. That will make things easier. So each bar here corresponds to a pair of critical points. Now I will do some thresholding by persistence. And I will rescale here with this button. And basically I will remove all the critical points with a persistence lower than 0.01, which is lower than 1% of the function range. And here we go. And actually tiny feature has been deleted here. So once we have this, we'll call the topological simplification filter that will take a function and keep only the critical points that we selected here. So we currently have a selection in the main view of critical points, and we'll use this as constraints to reconstruct in a combinatorial way the function, but without the noise. So we click on apply. All right, and we can look at this function. Visually, it looks pretty much similar, but here we have a noise-free version of that, of the function. So now we can compute the Morse Smale complex, this, and we click on apply. So here's the initial separate, so we can show the different critical points here. And for this, we'll call the spheres on this output, so we'll select the critical points. And we call the sphere from point, and we put 0.01 for radius. All right, and we'll use the color that is defined by the criticality of those points. So in green you have maxima, in blue minima, and white saddles. Okay. So now we'll display the separatrices, we'll smooth them a little bit before doing anything, all right? And then we'll represent them with tubes, but for this we need to convert the actual separatrices into data type that PowerView likes for the tube. Right now the separatrices are represented with a very generic mesh type, so we'll specify that further by transforming this into a surface type only. So for this, you type extract surface, apply, and then you can call tube. And here we'll put a radius, let's say 25, like this. All right. So now we can have a look at the segmentation. For this, we can select the Morse Smale manifold. So here you have one color per cell. So by default, you may have some cells that have similar colors next to each other. So you can randomize this a little bit with the TTK randomizer. And we'll say that we want to randomize the identifiers of the cell, like this. And basically the colors have been assigned randomly. And now you may want to compute the normals to have smoother shading. So for this, you need to convert into a surface type again, from a general mesh representation to a surface representation. And now you want to compute the normals, generate surface normals. And here you are. All right, so this is smooth shading. So at this point, what we want to do now is to compute the quad mesh out of the Morse Smale complex. So here I'll use this button to split the view into two. All right. And here I will select the Morse Smale complex, in particular the segmentation, and say that I want to compute the Morse Smale Quadrangulation out of the Morse Smale complex. And I will hit enter. So here you need to specify where's the surface that you want to quad mesh. This is this guy, the surface out of the Morse Smale complex. You need to specify by clicking here where are the critical points of the Morse Smale complex. You need to click here to specify where are the separatrices. And you click on OK. And here we want the dual quad mesh. All right. So we'll link the view by doing a right click in this view, do link camera, and we'll click in this view here. So at first the quad mesh is very coarse. So what we'll do is that we'll refine it. So we go for subdivision, quadrangulation subdivision. And we need to specify where is the input surface, this is the segmentation, and where is the coarse quad mesh, which is the Morse Smale Quadrangulation here. We click on OK. And here we may want to put relevant values. So let's put 1 and 10 first. We click on Apply. All right. And if we want to see the actual edges of the quad mesh, we need to select Surface with Edges here. And here it is. And we can further subdivide it if we want. Let's say 2 and 50 iterations of smoothing. All right. And we may want to show the extraordinary vertices of the mesh. So for this, you'll select in the pipeline the quadrangulation subdivision, and you'll go to Edit, Find Data, or you can press the keystroke V. Basically, you will say that you want to select the points of the subdivision for which the valence is greater or equal to 5. You do the query, and then you extract the selection. Click on Apply. So these are the points that have a valence higher than 5. And we'll do the same with those points with a valence lower than 3. So we selected the thing, and we run the selection again in the pipeline. All right. So basically at this point, those two items of the pipeline represent the extraordinary vertices. We'll select them both by keeping the key Control pressed, and we'll click here. And then we'll call the Append Dataset filter to make only one dataset out of this. Fine. So we grouped those outputs somehow, and we'll compute spheres for these points with a radius of 0.01. All right, and we'll color this by valence. All right, and here we'll show the quad mesh. Here we are. So above 4, this is dark green, and below 4, this is light green here. All right, so this concludes this tutorial. Thanks for watching.